Hi chemists, in this video we're going to look at how to interpret mass spectra and what do they mean, okay? So last video we looked at how a mass spectrometer works. Now we're looking at the information that it spits out at us and how we can work that back into going, that was the molecule that was put in. So first up I'm going to take you through what it means, and we're going to use this mass spectrum for pentane, okay? I found it online. We'll just use this nice example for a nice simple molecule, pentane, 5 carbons long. Okay, so just a reminder that the x-axis is the mass to charge ratio, and you can pretty much presume that anything that we'll encounter in our course has a charge of +1, and so we're going to treat it as a mass axis or a mass spectrum, just the grams per mole. Okay. The y-axis is the relative abundance, and remember the largest peak is set at 100%, and we call that the base peak, okay? And that's the most stable peak, and the lower peaks, the smaller the peak, the more unstable that fragment was when it came to the detector, okay? Not many of it were there. Now, the peak with the largest mass to charge ratio here, and in our case here for pentane it's 72, is called the parent ion or the molecular ion. And this is the original molecule minus electron, or it's the M plus radical fragment, okay? Now, this isn't always true in real life, okay? In real life, you can put your sample in, and this, your charge radical of the original molecule, may be so unstable that you actually don't see a blip for it on your mass spectrum. Okay, that is a possibility, but simple wise and for beginner wise, when you're looking at a mass spectrum, they'll always give you something that gives the parent peak. Okay, so that gives you a really good hint about what this molecule could be all along, because you just look for the peak furthest to the right and go, oh, that's the parent peak. That must be the molar mass of the molecule, okay? And let's check that. I think I'd do that on the next page, yeah. So we can check that. So that's one handy little hint for beginner people looking at mass spectrum. Whenever they're giving you a problem, the most furthest peak, the heaviest peak on the right will be your parent peak, which will be the same mass as the molecule they're looking for. So here, let's just check that. Okay, so a molecular ion or a parent ion is 72. So if we calculate the molar mass of pentane, we've got 5 12s. So 5 carbons plus 12 hydrogens gives 72 grams per mole. That's why we're seeing this peak at 72. So the parent ion is C5H12 plus and radical, okay? So it's pentane that's been bombarded by electrons and it's lost 1 electron. So it's got an unpaired electron and a positive charge, or I've drawn the structure up here, okay? All right, if we take a look at the next highest peak, the next major one here is at 57 mass to charge. We can deduce what this fragment is, and we can usually deduce it by the loss in mass, or the difference between it and the parent ion. So here we've got 72 down to 57. It's a drop of 15 mass to charge, or 15 grams per mole, okay? And this 15 grams per mole, or the mass to charge 15, comes up so many times in mass spectrometry of organic compounds because it's the loss of a CH3. Okay, so what's actually happened is we've formed this parent ion. It's been relatively unstable, and a proportion of the fragments have been this breakage. That bond breaks, and what you get is that CH3 radical. It doesn't go around the bend of the magnet because it doesn't have a charge. It hits the wall and falls out. Doesn't reach the detector, but the rest of it, as a charge, goes around the curve and reaches the detector, and it has a mass of 57. Okay, so what's left is the butane cation C4H9. Okay, so we've got a break in there. So some of the fragments broke and they lost a methyl group, as a radical, okay? And that's what we're seeing, that 57 peak. We're seeing this go around and hit the detector, okay? As we move down, let's try to identify what fragments the 43, okay? So 72 minus 43, or the start to 43, is a loss of 29 mass units. And that is a loss of 15 plus 14, okay? Now, a good hint with organic molecules, a loss of 15 is usually a CH3. Once the CH3 is gone, though, the things that come after that, if it's a carbon chain, is a CH2 or a 14. So a 29 loss is often a CH2, CH3 loss, okay? So we've got a break here in our molecule. So to produce this 43 peak, we've lost like an ethyl radical. And what we've actually seen is a propyl cation that's gone around the curve and reached the detector. And one thing to note too is this 43 is the base peak. It's the most stable. So it's saying when you form this parent ion radical, the pentane parent ion radical, the most stable fragments, the most stable breaking apart is this. Well, it's not really in half. It's a propane branch and an ethyl branch. Okay, and ethyl, that's the most stable, and that's why it was at 100%. Okay, let's go down to 29. We've lost 43. So what we've done is lost another 12. So we've lost another 14. So let me just write 15, 14, and 14. 15, 14, and 14 equals the 43, doesn't it? And so we've got a break on this side now. So it's kind of like it's reversed, it's mirror image. Now we've got like an ethane radical, and we've lost we've got an ethane ion, positive ion, that's gone around the curve and reached the detector, and we've lost this radical, a propane radical, that's hit the wall, and when it's curved and not reached the detector. Okay? So here I'm just presenting that information in a nice handy table. Sometimes you'll see this, sometimes you might be able to fill it in. What we've listed is the mass to charge of this major peaks, and we've determined the fragment that's been detected, okay, the positive fragment here. So for the 72, it was just the parent ion, the parent cation. And then for 57, it was the loss of a CH3. So see how it's got fragment lost? Nothing. And this one's lost a CH3 radical. The 43 is the 3 carbons, and it's lost the 2 carbons and the 5 hydrogens, and so on and so on. And I've just labelled here the parent ion or the parent peak, and the base peak as well. It's a good way to summarise your information. Okay, mass spectrometry can be a little bit hard to think of. Why are you getting all these peaks, and what does it mean? Are we getting these in molecules? It can be quite confusing. And I remember at university, I thought of this kind of analogy. I don't know how well it works. Some people have told me it's not too bad though. Okay? I like to think of mass spectrometry as trying to reconstruct a plate or a plate design from a box of broken plate pieces. Okay? So you've got a box of plate pieces. They're all crazy and smashed up there. And you're trying to reconstruct, hey, what did the original plate look like? Okay? So someone's carrying a box full of plates, and they've tripped over and smashed. Don't you love how you can find a stock image of absolutely anything crazy? I don't know what this stock image is for. Look at that poor guy who's changing the channel and about to be hit by plates. Confusing. So our task is to find out how the plate originally looked like, or in the analogy, what the molecule is from our box of broken pieces of plate, or our cation fragments, okay? But there's also this weird rule that you can only get one piece of the plate, of a broken plate, in your box. All the other pieces have gone. I don't know how to work that in an analogy. Okay, so some pieces who haven't got a large hit are going to be pretty much the whole plate, but with a small chip on the side, okay? And they're going to tell you a lot of information, aren't they? So I'm using that analogy. It's like we got our parent ion. We've just got one electron lost. We can go pretty much, hey, look at this. This is the original molecule. while a lot will just be smaller pieces as well, all the other fragments that we see on the spectrum, okay? But we can't glue all the pieces back together to make a new plate because they're all just random pieces from one individual plate, if that kind of makes sense. Let me know how that analogy goes. Give me some feedback on it. Okay, so here I've got another mass spectrum to show you. This one's of ethanoic acid, old name acetic acid. I've given you the structure here. You can see that the parent peak here is, I'm laughing because there's a little peak after that, and I'll get to that. The parent peak here is 60. There's a little blip on 61. I might just bring it up now anyway. So what we do, and what's good about a mass spectrum, is we start detecting isotopes. Okay, so I'm calling 60 as our parent peak, and I know it's a bit dodgy because there's one higher than that, but this 61 is due to, in our sample, we've got some isotopes, okay? We've got some heavy isotopes. We've got some heavy isotopes of carbon happening occasionally. We've got some heavy isotopes of hydrogen, or we've got some heavy isotopes of oxygen happening occasionally, and it's very rare, but it's enough to put a blip on the 61, okay? But I'm going to call our parent peak as 60, okay? We'll talk more about isotopes soon here too. Mass spectrometers are brilliant for detecting isotopes. So we've got a mass to charge parent peak of 60, and that relates to the molar mass of our whole molecule. So this 60 is just the charged radical, okay? It's the parent ion there. Our next peak is this 45 one. Is it this one here? Yeah, 45. And what you can see is that is a loss of 15. It's this break in here. We've lost a methyl group, haven't we? Yeah, loss of 15 organic molecule, you're looking at a loss of methyl group. Okay, there's also a loss of 17, and a loss of 17, usually in organic chemistry, you can go, oh, was there an alcohol group on there? And carboxylic acid alcohol, we've lost that OH group for the base peak. So that was the most stable, okay? So the weakest bond is this bond here. Okay, it produces the most stable. All right. After that, we've got a loss of the CH3 and O, and smaller. Okay. So there's some common fragments that I told you about, and we've kind of approached them. If you're seeing a loss of 15, it's a CH3 more than likely. There's not much else it can be. At 17, it's very, very likely that you've lost an alcohol group. 29, you're looking at you've lost an ethyl group on there. And then sometimes you see a 45, which is a loss of a carboxylic acid. Okay, on to isotopes. So sometimes isotopes, they can confuse you because you have a small little blip one above what your molar mass is, and you have to recognize that's probably just the isotopes of all the carbons and hydrogens there. Occasionally we're getting an isotope blip through, okay? But there's other ones that really help us out, okay? So chlorine has a molar mass of 35.45, and it has that relative molar mass because it has two isotopes, chlorine 35 and chlorine 37, with both relative high abundance. It's like a 3-to-1 ratio of abundances, and so you get these two peaks when you have chlorine in a molecule go through a mass spectrometer, and what you'll see is they differ by 2, okay, because 35 and 37 is 2, so you get like a double parent peak usually, but you get a double parent peak too, and you get a nice 3-to-1 ratio here. So this type of thing that you're seeing, not at 64 and 66, but 2 away and a 1-to-3, says, hey, I've very likely got a chlorine molecule here, and it also helps that it drops that much. Thanks, mate. See ya. The same thing happens with bromine. Okay, you've got bromine 79 and bromine 81. These exist in abundances around 50-50. Okay, so what you end up if you got a bromine in a molecule and you run it through a mass spectrometer, you get like a mass loss of 7981, but you also get this double parent peak that is 2 apart and pretty much equal in prevalence there. So that's a good indicator that you've got a bromine molecule there. Okay, let's talk about the positives and negatives of mass spectrometry. Might have kind of brought it up before. One of the most positives is it's sensitive. You only need a small amount of analyte, okay? And you can dissolve it to a very low concentration and it'll still find stuff. So usually you only inject into there microliters, okay? So very, very small amounts. So it's very sensitive. Another good hint, though, is these mass spectrometers are linked to computers, and the computers are the readout. They're also linked to very large databases of previous mass spectra, like large databases. And so these computer programs make predictions and compare it to mass spectra, so they can pretty much identify it for you. Now, it's still a really good skill as a student to work out how these work as well, because when problems happen, you can't always rely on that program to help you out. So you can get smaller instruments that I was talking about with that the Syria type, the scientists who went into Syria with those mass spectrometers that are about the size of a suitcase, and so you can get portable ones here, and that's why I put the Mars Curiosity rover here. You can see on the instruments there, you've got I think I put it in here. Here we go, X-ray spectrometer, those type of things working in there as well. Where's the mass spectrometer? I believe there's one in there anyway. Okay, negatives. Yeah, you need to have your sample with it, okay? You can't, I know it sounds weird, but you need your sample on the site with the instrument. Some spectroscopy, you can work at a distance, okay? And I don't think we really go into that with our course here, but you can, like a UV vis spectrometer where you can shine the light through a sample. A good example of that is we could take the atmosphere, the Earth's atmosphere as a sample, and we can shine a laser light through it up to a satellite or down from a satellite, and we can look at absorption through our atmosphere and measure the concentrations and what molecules are in our atmosphere. And that's happening all the time, of course. So that's what I'm trying to contrast it with there. We've got some spectroscopy techniques that we don't need the molecule to be in sight for. Okay, they're still bulky. Even the smallest instrument is about a suitcase size. So they're not perfect. No, they are perfect. They're wonderful machines. Okay, here's another negative, but we've turned it into a positive kind of thing. Mixtures, okay? If you get a mixture and you put a mixture through a mass spectrometer, you're going to get the peaks of all of the fragments of all of the things in there. You're just going to get a big, big mess. Now, luckily, scientists in I think about the 70s or 80s come up with an idea. Let's couple a mass spectrometer with a separating machine, okay? So we can put a mixture in it, we'll get separation of the components, and then they'll feed into the mass spectrometer over time. Brilliant idea. And it forms this instrument here that I've got a picture of, and this side's the mass spectrometer, and this side is what we call a gas chromatograph, okay? And gas chromatography. Chromatography, remember, is a separation method. There's lots of different chromatographies. Here we've got it in gas. So what's happening on this side is we inject our sample as a solution, as a mixture, and it gradually heats it up. And it heats it up over a set rate. And what ends up happening is as you hit a component's boiling point, that will suddenly go through a very, very long thin tube and feed into the mass spectrometer. And so you will only get stuff that is hitting their boiling point at a time, okay? So it's kind of like fractional distillation first. You're getting a separation technique and then fit into it. So a gas chromatography mass spectrometer, or a GCMS, is a very, very useful instrument. You can inject any mixtures in there. And these are the machines, they're very widely used, but they're the ones that you're seeing on like NCIS and all those other forensic shows. They're the type of things that can be that handy, like in the show, but not quite as handy in the show. They're very definite in their findings in the show. Okay, I think I've mentioned enough. So the negatives is you cannot use a good mixture, but you can couple it with a separating thing like gas chromatography, and it becomes this wonderful, wonderful thing that's used widely. Okay, past paper questions. The diagram shows a mass spectrum of an organic compound. Okay, which compound could it be? Notice our largest peak there, they've labelled 88. I know they've got an 89 there, but they've ignored it, saying that that's an isotope peak. So 88 is our parent peak. So which one of these has a molar mass of 88 grams per mole? Okay, so you just go through. Or should we work it all out? Have I got a calculator here? Why didn't I prepare? Okay, it can't be iron 2 sulfide because we usually don't put, we can put inorganics, but no, it's only got the two things in there. Okay, so butanoic acid, let's draw ethanoic acid and get a formula for it. So it's C2H4O2. So it has a molar mass of 2 times 12 plus 4 times 1 plus 2 times 16, which equals 60. So the largest peak we should see for ethanoic is 60. No, I mean the largest is in mass to charge. No, that's our base peak. It's not ethanoic acid. I see why they chose that distractor. That's a good distractor. If you don't quite understand that that's just the base peak, it's not, they could think that's ethanoic acid. All right, butanoic acid. What have we got? Butane, so C4H3 3, 4, 5, 6, 7, 8, C5H8O2. I'm not good at doing this in my head, and I shouldn't encourage you guys to do it. I'll draw it all out properly. Okay, there's our butanoic acid. Let's check how well I've done. C4H3, 4, 5, 6, 7, 8, and O2. Good, okay, I did get it right, but check yourself. Don't try to take shortcuts. You'll make a mistake. 4 times 12 plus 8 plus 2 times 16 is 88. Look at that. Let's just make sure butane 1 amine. 4 carbons. There's our amine on 1. So we're going to get C4, H3, 4, 5, 6, 7, 8, 9, 10, 11. And 1 nitrogen. Notice here, we're going to get an odd molar mass. And that can be quite a telling thing for simple numbers, for the whole, what am I looking for? For the parent ion, if your parent ion is an odd number, it's a good hint that it's a nitrogen in there for us. Because remember, we usually do with stuff with C to the N H2N or C to the N H2N plus 2 or 2N minus 2. So we're often looking at even molar masses. Okay, so without calculating that, I know that with 11 hydrogens and carbon being 12 and nitrogen being 14, that's going to give us an odd molar mass. So I can cross that out, but just for clarity's sake, let's calculate it out. 4 times 12 plus 11 plus 14, 73. Yep, it is odd and it doesn't match it. So it's definitely butanoic acid. So these type of problems are common. All you need to do is go to that parent peak, and they've labelled it here, and just check the molar masses of all your possible answers. Okay. Look, here's another past paper question. Here's another mass spectrum what is the compound? Let's find out what this peak is. And I've scribbled over my info there. Because trying to erase. Okay, let's count very carefully. So there's 40. So I'm guessing that's 41, 42, 43, 44. So I think that's the mass to charge 44. So we're looking for something with a mass of 44. Okay, ethane, C2H6, which equals 2 times 12 plus 6 equals 30. Is that it? No. Propane, C3H8, 3 times 12 plus 8 equals 44. I think it's propane. If it was chloropropane, it would be, well, 44 minus 1, get rid of the hydrogen, plus 30, 35, 37. So let's type in 35. It's going to have 78, so it will have a base peak up here. No. And remember, with a chloro, we'll see that 35, 37, that 1 to 3 peak, that's 2 apart. So it's not that one at all, no. Butane, it's going to be heavier, isn't it? C4H10, 4 times 12 plus 10, 58. It's definitely not that. So we've got propane there, okay? So now you've got enough skill to look at my worksheet there, and there's some extra examples from the textbook too. I hope that helped you out, and there's some other help from some lovely people online like Professor Dave and Bozeman Science there as well, and Khan Academy. Okay, next video we'll talk about NMR.